Welcome to this beginner-friendly tutorial on C-sharp physics and collisions in Unity. We'll explore how objects interact dynamically in your game world, covering essential concepts to create realistic and engaging experiences. This guide will provide a solid foundation for understanding Unity's physics system. Understanding physics is absolutely crucial for crafting realistic and engaging game experiences. It governs everything from fluid character movement to complex environmental interactions, making your game world feel authentic and responsive. Mastering these principles enhances player immersion and the overall quality of your project. We'll begin by setting up a basic scene in Unity, serving as our foundational workspace. This includes a simple player cube and a ground plane, allowing us to focus purely on physics concepts without visual distractions. This minimalist approach ensures clear understanding of each step in our tutorial. First, create a 3D cube and rename it Player for easy identification. Next, create a 3D plane and rename it Ground. This clear naming convention is a best practice for maintaining organization and readability in your project, making it easier to manage your game objects effectively.
Next, we introduce the essential rigid body component, a cornerstone of Unity's physics system. This component brings properties like gravity, mass, and velocity to your game objects, enabling them to be influenced by forces and torques. It allows objects to move, fall, and collide in a physically realistic manner.
The rigid body allows objects to be affected by forces and gravity, making them behave like physical objects in the real world. Without a rigid body, an object would remain static or move only through direct script manipulation, lacking physical realism. It's fundamental for dynamic and believable interactions. Key rigid body properties include mass, dictating how much force is needed to move an object, influencing its inertia. Use gravity determines if the object is affected by the scene's gravitational pull, causing it to fall naturally. Adjusting these values fine-tunes the physical behavior of your game objects. You can also adjust drag to simulate air resistance, slowing linear motion, and angular drag for rotational resistance, preventing objects from spinning indefinitely. These properties are vital for creating nuanced physics, like a feather falling slowly or a heavy barrel rolling to a stop, adding significant realism. For precise and consistent physics calculations, perform all rigid body operations within Unity's fixed update function. This function runs at a fixed time interval, independent of frame rate, ensuring stable and reliable physics simulations across different hardware. This prevents jittery or inconsistent behavior in your game, crucial for accuracy. Next, let's talk about colliders, an indispensable component in Unity's physics engine. Colliders define the precise physical boundaries of your objects, acting as invisible skins that detect interactions. They are essential for collision detection, allowing objects to register contact and react appropriately, whether hitting a wall or striking an enemy. Without a collider, even with a rigid body, objects will pass right through each other. The rigid body handles physics calculations, but the collider provides the physical shape for interaction. Therefore, a collider is absolutely necessary for any physical interaction or detection to occur in your game world. Unity offers various collider shapes like box, sphere, capsule, and mesh colliders, each suited for different object geometries. Box colliders are ideal for rectangular objects, sphere for spherical, and capsule for characters. Choosing the right collider type is crucial for both accuracy and optimization, ensuring efficient and realistic interactions. For our player cube and ground plane, Unity automatically adds box colliders upon creation. This default behavior is helpful because box colliders are perfectly suited for these simple, rectangular shapes, providing accurate collision detection without manual configuration. This streamlines the initial setup for basic physics interactions. Now that our basic physical components are in place, let's dive into scripting. We will use C# to write code that detects precisely when our player cube makes contact with the ground. This scripting capability enables us to define custom behaviors and reactions to these physical interactions within our game. Create a new C# script called Player Collision Handler in your project window. Then, drag and drop this script onto your player cube in the hierarchy. This attaches the script component to the player object, allowing it to execute the code we're about to write for handling collision events. Inside this script, we'll implement the onCollisionEnter event function. This Unity message is automatically called by the physics engine the moment our player's collider first makes contact with another collider. It's a powerful tool for detecting initial impacts and triggering specific actions when a collision begins. The onCollisionEnter function is called only once, precisely when two colliders initially touch. This single invocation makes it ideal for events that should occur just at the beginning of a collision, such as a hit event. It ensures actions aren't repeated for continuous contact. To verify our collision detection, let's add a simple debug log message within our onCollisionEnter function. This will print a message to the Unity console, confirming when our player cube successfully hits the ground. It's an invaluable debugging tool for understanding event flow and script execution. When you run the game, observe the console window. As the player cube falls and makes contact with the ground, you will see the debug log message appear. This visual confirmation is your immediate feedback that the onCollisionEnter event has successfully fired, indicating your script is functioning as expected. Beyond onCollisionEnter, Unity provides onCollisionStay, called every physics frame while colliders are in contact, useful for continuous effects. OnCollisionExit is called once when colliders stop touching and separate, signaling the end of a collision. These events offer comprehensive control over various collision states. Now, let's explore triggers, a distinct concept in Unity's physics system. Triggers are designed for detection without physical interaction or repulsion. They allow objects to pass through each other while still registering their entry and exit, opening up a wide range of gameplay possibilities for your game. To make a collider a trigger, simply select the object, navigate to its collider component in the inspector, and check the isTrigger box. This alters the collider's behavior, allowing other objects to pass through it while still enabling detection events. The collider's wireframe will visually change to a dashed line. When isTrigger is enabled, objects can pass directly through each other without physical collision. Their entry and exit from the trigger volume are still precisely detected by Unity's physics engine. This allows for non-physical interactions, such as picking up items or activating zones, without blocking movement. This non-physical detection makes triggers perfect for many gameplay scenarios. They are ideal for collectible items a player can walk through, activation zones that trigger events upon entry, or detecting when a player enters a specific area. Triggers provide flexible interaction management without physical blocking. Let's create a new cube, rename it Collectible, representing an item our player can pick up. We will then set its box collider to isTrigger in the inspector. This setup ensures our player can pass through it while still registering an interaction, demonstrating a common use case for triggers. Now, we need to modify our player collision handler script to use the onTriggerEnter event function. This function detects when another collider enters the trigger volume of the object this script is attached to. It allows us to handle trigger-based interactions distinct from physical collisions. Similar to onCollisionEnter, onTriggerEnter is called once when a collider first enters a trigger zone. This single invocation is perfect for events that should happen immediately upon entering an area, such as granting a power-up or initiating dialogue. It ensures the action is performed just once per entry. We'll add a debug log message within our onTriggerEnter function to confirm trigger detection. This message will print to the Unity console, indicating when our player successfully enters the collectible trigger zone. This provides immediate feedback and helps us verify that our script is correctly identifying trigger interactions. When you play the game and move the player cube into the collectible object, you will observe the debug log message in the Unity console. This confirms that the onTriggerEnter event has successfully fired, indicating your player has entered the trigger zone. This visual feedback is crucial for debugging. Just like with collisions, triggers also have onTriggerStay and onTriggerExit events. OnTriggerStay is called every physics frame while a collider remains inside the trigger volume, useful for continuous effects. OnTriggerExit is called once when a collider leaves the trigger zone, signaling the end of the interaction. These events offer comprehensive control. For performance optimization in complex scenes, consider using physics.overlapsphere or physics.boxcast for broad phase collision checks. These functions efficiently query for colliders within a volume or a long array, without relying on individual on-collision or on-trigger events. They are excellent for checking for enemies or obstacles, reducing computational overhead.
Always ensure rigid bodies are attached exclusively to moving objects that require physics simulation, not static environment pieces. Attaching rigid bodies to static objects forces the physics engine to constantly reevaluate their positions, leading to unnecessary computational overhead and potential performance bottlenecks in your game. This is a critical optimization for efficiency. Utilize Unity's tags and layers to filter collisions and triggers. By assigning specific tags or placing objects on different layers, you can configure the physics engine to ignore certain interactions between groups of objects. This filtering mechanism prevents unnecessary checks, significantly improving efficiency and control over complex interaction logic.
Maintain clear and concise code, especially when handling multiple collision or trigger events. Well-structured code with meaningful variable names, comments, and organized functions makes it easier to understand, debug, and expand your game's logic. This practice ensures your physics interactions remain manageable and scalable as your project grows. Carefully choose between collision and trigger detection based on your specific needs. Use collisions for physical interaction, like objects bouncing or characters being blocked. Opt for triggers when you only need to detect an object's presence without physical impedance, such as collecting items or activating zones. This distinction is key.
In summary, we've covered setting up a basic scene, understanding rigid bodies and their properties, and exploring colliders and their various shapes. We then mastered scripting collision events like on-collision enter and trigger events like on-trigger enter. This foundational knowledge equips you with tools for creating dynamic and interactive game worlds. You now have the foundational knowledge to implement robust and dynamic physics and collision systems in your Unity projects. From making objects fall realistically to detecting complex interactions, these skills are essential for creating engaging and believable game worlds. This understanding opens up a vast array of possibilities for your game development.
To truly solidify your understanding, experiment extensively with different rigid body properties, collider types, and scripting scenarios. Hands-on practice will deepen your knowledge, reveal new possibilities, and help you develop an intuitive feel for Unity's powerful physics engine, fostering creativity and problem-solving skills. Remember, mastery comes with consistent practice and exploration. Keep experimenting, building, and pushing the boundaries of what you can create with Unity's physics system. With dedication, you'll soon master the intricate art of physics-based interactions, bringing unparalleled realism and excitement to all your game development projects.